Today's lesson is on proving congruence. We're going to see that as we make rigid transformations, the shapes will keep their shape and their size. So let's start with number 1. It asks us to translate polygon A so that point P goes to point Q. In the image, we're going to write the length of each side in grid units next to the side. So if we start with polygon A, a couple ways we can do this. One of them is I can use my patty paper and I can trace polygon A. And I know that I need to now translate it so that point P goes to point Q. And I'll be able to see exactly where polygon A should land. The other way is, of course, if you don't have patty paper, you could just look at the shape and see that from point P it goes back 2 units, down 2 units, over 1 unit, down 3 units, over 2 units, up 4 units, to the left 1 unit, and up 1 unit. And we'll see that all of the side lengths of polygon A and its translated polygon are the same length. This side is 3 and this side is 3. This side is 2 and this side is 2. We went up 4, left 1, up 1, up 1. So we can see that all of our side lengths are the same. Therefore, polygon A and its translated image are congruent. Let's look at number 2. It asks us to reflect pentagon C across line L. Once we reflect it, it asks us to mark the grid units on the outside and also the angle measures on the inside. If we use our patty paper to trace pentagon C, I'll include the measure of each angle. And I need the line of reflection or some point of reference so that when we reflect, we'll be able to use that line or point of reference to see exactly where polygon C's reflection will land. So if we trace, I'll see that polygon C's reflection is right here. And the measure of the angles, of the corresponding angles, must be congruent. So this angle here at the top is 90. I can see that it's 90 degrees on the bottom. If we move around, this is 120 degrees, followed by 90 degrees, and ending up here with 150 degrees. So corresponding angles are congruent. The side lengths, the top is 2 and this top is 2 units. Coming down the side here is 3 units and this is 3 units. Across here is 2 units and across here is 2 units. So we can prove that polygon C and its reflection are congruent. All side lengths are congruent and the measure of all angles are congruent. Continuing on to the next page, we see that we have a grid showing triangle ABC along with 2 other triangles. It says that you can use a rigid transformation to take triangle ABC to one of the other triangles. The question is which one and how do you know? So if we look at triangle ABC, we're asked how can we move that, or which triangle can we move to get this triangle on top of one of the others. So if I use some patty paper to trace triangle ABC, and I try to move it to get it to, let's say, triangle EBD. Looks like I would need a rotation to get one on top of the other. But even when I rotate 180 degrees, I see that it doesn't fit exactly on the top. That's because these 2 triangles are different sizes. They are not congruent. Therefore, there is no transformation that will allow me to get this triangle onto this triangle, because they're 2 different triangles. This side length here is 2 lengths and its corresponding side is 3 lengths. So we can see that they're not going to be the same. So let's give triangle CFG a try. So if I go back to my triangle, I can see that I can rotate my triangle 90 degrees clockwise, and then I can translate it back some units or forward some units so that triangle ABC is directly on top of CFG. So which triangle can we perform a rigid transformation to get ABC to? Well, that would be to angle CFG. How do I know? I know because they are congruent triangles. Congruent, again, meaning same shape, same size. The next question asked to describe that rigid transformation of how we got triangle ABC over to triangle CFG. And again, if we place this on top, we saw that we could rotate it 90 degrees clockwise, and then we could slide it to the right. And when we slid to the right, we went 1, 2, 3, 4, 5, 6, 7. So we said we could rotate 90 degrees clockwise. We always need to know how far and in what direction. And then we slide to the right 7 units. Okay. Let's take a look at another question that asks, is there a rigid transformation that will take rhombus P to rhombus Q? Well, if we trace rhombus P, and I look for a way to slide, rotate, or reflect to get P to Q, we'll see that there's no way possible because they're two different shapes. So is there a rigid transformation? Is there any form of transformations that will get P to Q? The answer is no, because they are different shapes. One last question asks us to describe a rigid transformation that takes triangle A to triangle B. So we have two different triangles here. Here's triangle A, and it shares a line here with this side of triangle B. And the question is, how can we get triangle A to triangle B? So if I trace triangle A, I'm looking for what movements can we make? Slides, flips, and turns. And I see that I'm not going to have to turn it at all. I'm definitely not going to have to reflect it or flip it over anything. What we're going to have to do is slide it. The question is how? So if I want to get this point here of point A to its corresponding point right here of B, we can see that we'd have to go 1, 2, 3 to the left, 3 to the right, and 2 up. So if we were writing that in our translation notation, we would take x plus 3 and y plus 2. Remember, this means that we're moving 3 up, or 3 across the x-axis, and this means that we're going 2 up the y-axis. Okay, there's some practice problems for you on the next page, so please continue.